Okay, this is a little video on freezing point depression and boiling point elevation. So, you know what these words mean. Depression means we're coming down, and elevation means we're going up, right? And we're talking about the freezing and boiling point of aqueous solutions. And if you remember that an aqueous solution is pure water mixed with some sort of a solute, okay? And water by itself has its own freezing temperature and boiling temperature. So the accepted values here for water freezing is at 0 degrees Celsius and boiling at 100 degrees Celsius, okay? But once we start mixing stuff into it to make aqueous solutions, we're going to freeze that solution at a temperature less than 0, below 0, and that solution will boil at a temperature above 100. So that's what we mean by freezing point depression and boiling point elevation. We can depress or lower the freezing point of water by adding a solute to it, and we can elevate or raise the temperature of that water would boil by adding a solute to it as well. Okay, so how far below 0 and how far above 100 depend on the type of solute that's in the solution and the molality of that solution. And remember that molality is the concentration that we're gonna use because we've got a temperature that's very clearly gonna be changing temperatures, and we wanna be able to have a consistent concentration, and molality will not change with temperature like molarity does, okay? So, like everything, this has a math equation that goes along with it. Okay, so here it is, delta T equals I K M. So there's some unfamiliar variables to you. Okay, delta T, this is the number of degrees either above 100 or below 0 that the solution will change to. So this is usually going to be a pretty low number. And then M is the other one that you might know already. This is the molality. And remember that molality has its own equation, and that's moles of solute over kilograms of water. Okay, K, this is a new variable for you. This is a constant number that gets used in these equations, and actually there's two different constants here. So if you're working with a boiling point question, K boil, the number that you're going to use here is 0.512. All right. Now, if it's a freezing point depression problem, K freeze, we'll call it, then the number you're going to use is 1.86. Okay, so you'll use a different number based on the type of question that's being asked of you. Now, I, this is the kind of the goofy one. This is known as the Van't Hoff number. And Van't Hoff was a Dutch chemist. That's why this name is kind of funny. Anyway, we don't care much about him, but let's talk about what that number means here. Okay, so the Van't Hoff number. This is the hardest one for students to deal with. All right. So the Van't Hoff number, if we're talking about ionic compounds, and this is specific to the solute, okay, not to the water. This has to do with the stuff that's getting mixed into the water. So if it's an ionic compound, which can be identified as a substance that's a metal bonded to non-metal, if it's an ionic substance, then the Van't Hoff number is a sum of the subscripts from the chemical formula. All right, so if we look at a couple of examples of ionic compounds here, like sodium is a metal, chlorine is a non-metal, they sum up to 2. Remember, there's a little invisible 1 on each of those things. Magnesium chloride, also ionic. 1 magnesium and 2 chloride ions gives us a total of Van't Hoff number of 3. And then a more tricky one is like this, copper 2 phosphate. And so we have 3 copper ions and 2 phosphate ions for a total Van't Hoff number of 5. Okay, that's for ionic compounds that will dissociate into ions. So those guys dissociate into their individual ions. If it's a covalent compound that is a solute, then the Van Hoff number is 1. And remember that covalent compounds can be identified by just having all nonmetals in their chemical formula. And so here's a few examples of some types of solutes that you might see. And you can see that all of the elements that make up these compounds are nonmetals. And so every one of these things has a Van Hoff number of 1. All right? And that's because they don't dissociate. You know, they will just sort of dissolve into individual molecules, but they don't come apart into individual carbons, hydrogens, and oxygens, or anything like that. So don't add up the subscripts of covalent compounds. The Van Hoff number for these guys is always just 1. All right. So let's look at a few practice problems ranging from pretty easy to a bit harder, and see how we can use this equation to solve these things. So this first one is about as easy of a type of question you'll see. What is the freezing temperature of a 1.7 molal solution of calcium chloride? Okay, so let's start with our equation and we can see what it is that we have. So our equation is delta T equals I times K times M. All right, so let's try to think what it is we have. So starting with I, which is based on the solute calcium chloride, CaCl2, that has a Van Hoff number of 3. We always have K. For a freezing temperature question, it's 1.86. And we've been given the molality of the solution here, which is really nice, and that's 1.7. Okay, so that just means that the only thing we don't have is our delta T, which is what we're solving for. All right, so let's multiply these numbers and see what delta T is. Okay, we're going to call that 9.5. So delta T equals 9.5. Now the common mistake is just to circle this as your final answer and just be done with it. But remember that delta T is the change in temperature below 0. So it's how far away from 0 it's going to be. And so because we're depressing the freezing point, we're bringing it 9.5 degrees below 0. So our final answer here is actually negative 9.5 degrees Celsius. All right. Okay, let's do another one. This one's a little bit trickier. What is the freezing temperature of a solution made by mixing 0.75 moles of sodium chloride with 0.5 liters of water? So again, let's start with the equation and see what it is we have and what we're solving for here. So delta T equals I K M. Okay. So we have, again, with sodium chloride, NaCl, that is a Van Hoff number of 2. This is a freezing point question again, so we're 1.86. And the molality, this one is a little bit trickier. We don't have the molality in the problem, but we have the numbers that are going to get us the molality. So we have 0.75 moles divided by a number of kilograms of water, which equates to liters, right? So this is 0.50 kilograms of water. Remember that molality is just where you divide the moles of solute over kilograms of water. So we actually do have M, we just had to kind of dig for it. So 0.75 divided by 0.5 gives us a 1.5 molal solution. Okay, so again, we're just solving here for delta T. Okay, and this again is going to be a number that drops down below 0. So even though we're going to calculate a positive number here, we're going to make it the negative because it's the amount of degrees below 0. Okay, so let's multiply. So delta T equals 5.58 degrees. I'm going to call that 5.9 degrees Celsius. And we got to take that down below 0, so that's actually negative 5.9 degrees Celsius. Okay. Usually the tricky stuff comes with the molality part of this, which in the next couple of examples, that'll become very clear. Okay, next question.